All right, we're at section 13.4, Kepler's Law and the Motion of Planets. This is a very interesting section, kind of a fun section, I find. Let's share the PowerPoint. And the first image here, there's a really kind of a historical background that they're going to introduce. Claudius Ptolemy, um, the presented a model of the Earth being the center of the solar system. In other words, it's called the geocentric model, um, where the geo meaning the Earth, geocentric. It was the center of the Earth, and everything revolved around it. And it, for the most part, it's kind of what we observe, and it kind of made sense, and it was accepted for many years. Um, there were some problems though when the some of the planets uh, seemed to go backwards. They would have what is called retrograde motion, so they would appear to be going in one direction, especially like Mercury and Venus. They would go in one direction, and then they'd seem to back up, and they developed um, a whole theory of how these planets had these uh, uh, epicycles around the Earth to describe this retrograde motion, and that really didn't. Um, it was a complication that had to be introduced to stay with this model, that the geocentric model, and then along came Copernicus, um, Nicholas Copernicus, and he said, okay, the Earth isn't the center, the sun is the center. And he was afraid to publish it because of the church stood by the Ptolemaic model, and so he would have been going against the church's teaching had he. So he was a little hesitant to publish it. Uh, but Copernicus came up with the heliocentric model, helio being the sun, where the sun is the center and all the planets rotate around the sun, and you no longer had this problem with retrograde motion. Everything kind of fit into place, so it made a lot more sense. Then we have Tycho Brahe. Tycho Brahe is a very interesting fellow. um, if you look him up in Wikipedia, uh, he was kind of an eccentric individual, but what he did was he even had a, they think he had a brass nose. Apparently, he had his nose cut off in a duel with a sword, and had a copper or a brass nose fitted, um, to replace it. But he was a dedicated um, studier, student of the stars and planets. Now, this is you have to understand that this was before there were any telescopes. He would just do it um, by just observing the uh, uh, the stars, and all he used was a sextant and a compass. There were no telescopes, but he kept very detailed notes on the positions of the planets. And it says that 777 visible stars at the time. He kept very detailed notes. He didn't have any theories, but he kept very good notes. His assistant, Johannes Kepler, uh, took studied his notes and tried to find reasons why there was uh, why these movements of the planets and the stars were the way they were, and he came up with our three Kepler's laws of planetary motion, and these are the three laws. All planets move in elliptical orbits with the sun at one focus and empty space at the other. There's nothing at the other focus. The radius vector drawn from the sun to a planet sweeps out equal areas in equal time intervals. We're going to need some graphics to show this. And then the square of the orbital period of any planet is proportional to the cube of the semi-major axis of the elliptical orbit. The square of the orbital period of any planet is proportional to the cube of the semi-major axis of the elliptical orbit. Bottom line, the further out a planet is, the longer its period is, the longer it takes to orbit the sun. Mercury, who's Mercury in Greek mythology? He's the messenger. He was the fastest. So our planet Mercury goes around the sun about 4 times for every 1 year that it takes us to orbit the sun. Mercury, he's fast. That's why they named the planet Mercury, because it goes around the sun very rapidly. Pluto, if you accept, whether it's a planet or not, Pluto's, I forget its orbital period. It's in the hundreds of years. It takes hundreds of years to circle the sun. What we do in 1 year, it takes hundreds of years to circle the Earth. Let's keep going. Now, let's look at the elliptical orbits. Now, an ellipse is defined by the semi-major axis and the semi-minor axis. A, you can see it on here. This is A, the semi-major axis, and then the B is the semi-minor axis. And there's 2 foci. Each focus is located at a distance c from the center. You can see C there. Now, this is this is an ellipse, but when it comes to the orbits of the planets, this is very exaggerated. Most people accepted the fact that the planets were circular orbits, and it was Kepler that he struggled with this because it didn't fit into a circular orbit, and he's the one that discovered that, well, they're ellipses with the sun at one focus and empty space at the other. Let's change. Oops, I went back. I need to change. Let's do a new share of, what am I trying to share? I'm trying to share, there it is, the preview. Okay, I've got this same graphic. I put a big yellow dot where the sun would be, and so F2, the sun is at F2, and F1, it's empty space. There's nothing there. So when an object is far over here to the left, the distance from the sun is A plus C, the semi-major axis plus C, the distance from the center line to the focus, and that's called aphelion. Some people say aphelion. I prefer aphelion, helio being the sun. I must come from being opposed. I don't know my Latin that well, so I'm not sure whether it's Latin or Greek, but it means like opposite the sun, aphelion. If you're talking about the Earth and a satellite, it's at apogee. G being geo, coming from geo. Apogee for the Earth, aphelion for the sun, so it's at its furthest point, aphelion. Over on the right, perihelion, it's when it's closest for a Earth system, a satellite around the Earth. Instead of perihelion, we say perigee. Again, the G being the geo from Earth. Now, one of the characteristics of ellipses is their eccentricity. Now, as you move those foci closer and closer together, it gets closer to it gets closer to a circle. And the eccentricity is the ratio of the C over A. So if C is 0, C over A is 0, so a perfect circle would have an eccentricity of 0. As you go further and further out, the eccentricity gets closer to 1. So it's always going to be between 0 and 1. The Halley's Comet, it has a eccentricity of 0.97. It's a very elongated uh, ellipse. The Earth's eccentricity, I think, is 0.017. It's very small. It almost appears to be a circle, but it's not. It's a slight um, uh, ellipse. Now let's. I have to switch back to the. Okay. So let's get back. The sun. Okay, here the sun is located at a focus of the ellipse. There's nothing physical located at the center, the black dot, or the other focus, the blue dot. Here that it's talking about the orbit of Mercury. I don't know what Mercury's eccentricity is. It probably shows in the table. There's Halley's Comet. It has an eccentricity of 0.97, very, very elongated. So let's see. Did I go back or no? Okay. So Kepler's first law is that the planets travel in an ellipse. Let's see, why are they showing it twice? What am I missing? Okay, no, they just go through the definitions of aphelion, apogee, perihelion, and perigee. Let's see if there's anything else I need to discuss. Okay, Kepler's second law is that planets mark out the radius vector drawn from the sun to a planet sweeps out equal areas in equal time intervals. So the area swept out by R in a time interval dt is half the area of the parallelogram. You can see this here. So the angular momentum, the change in angular momentum is equal to 0. So angular momentum is constant for planetary motion. L is equal to R cross P, where P is equal to the linear momentum, and that's equal to M, the mass of the planet, times R cross V equals L. L equals the mass of the planet times Rx V, the radial vector times the velocity vector. Now, the dA, the area, is equal to 1/2 Rx dr equals 1/2 Rx V dt equals 1/2 Rx V dt. So the d area is equal to 1/2 the magnitude of the angular momentum over the mass dt. So dA dt is equal to L over 2m. What I want to show, and I may have trouble getting there. Hopefully, I have it up. Let's see. You're not seeing it, I'm sure, because oops. And indulge me a moment while I find a nice graphic. Kepler's laws, because this is a good graphic that demonstrates what's going on. Let me see if I can bring it up. I'm just going to Wikipedia because Wikipedia has a very, very nice graphic. So let me come to a new share and find the here it is. Now, I like this graphic because it really shows what's happening. Now, think about throwing a ball up in the air, right? You throw a ball up in the air, what happens? It reaches a peak and it comes back down. And that's one of the explanations for what's going on in Kepler's second law. They're showing there, you can see the purple area on this graphic is the equal area that they're talking about for a time interval. Well, what's happening? Why is the area equal? Look at the tangential velocity vector, which is green. The tangential velocity vector is largest when the planet is closest to the one focus. So at that point, like I said, you think of to the right end is like the ball being thrown up in the air. It slows down and it comes back down. So this is a beautiful picture of an exchange of potential energy and kinetic energy. The maximum potential energy is when the planet is far from the sun. The maximum kinetic energy, you can see that the tangential velocity vector is largest when it's on the left-hand side, when it's at its closest approach. That's when the velocity is greatest. That's when the kinetic energy is greatest. So it's a constant exchange of potential energy on the right-hand side to kinetic energy, maximum kinetic energy on the left-hand side. And guess what? The total energy is zero. It always stays the same. But let me read the text here. The same blue area is swept out in a fixed time period. The green arrow is velocity. The purple arrow directed towards the sun is the acceleration. The other two purple arrows are acceleration components parallel and perpendicular to the velocity. So thank you, Wikipedia. This is a very nice graphic demonstrating Kepler's second law, that the an equal area is swept out for equal time intervals. And the reason is this exchange between potential energy and kinetic energy. Kinetic energy at the left-hand side, potential energy on the right-hand side. Okay, let's go back to the PowerPoint. All right, so you can study this all you want. I like the graphic on Wikipedia because it tells you what's happening. Okay, Kepler's third law, the square of the orbital period of any planet is proportional to the cube of the semi-major axis of the elliptical orbit. And bottom line, again, is just saying that the further out a planet is, the longer its period. So let's go. F of g is equal to mass of the planet times the acceleration. The force is equal to g. This is Newton's law of planetary universal gravitation. G, mass of the sun, mass of the planet divided by r squared. Mass of the planet equals mass of the planet. V squared over r is the v. What is v squared over r? That's the centripetal acceleration. Okay, so we get GMS over r is equal to 2 pi r divided by t, which is the period, over r, and square that, square the numerator. T squared is equal to 4 pi squared GMS r cubed is equal to ks r cubed I'm not going to hold you all responsible for this. The period t squared is equal to 4 pi squared GMS a cubed equals ks a cubed. So, and what that says is the square of the orbital period t squared of any planet is proportional to the cube of the semi-major axis of the elliptical orbit. That's what the A is. The cube of the axis. Okay, and here's some. Oh, I wish they had eccentricity here. You can see this t squared over r cubed is very consistent. 2.98 for Mercury, 2.99 for Venus. All of these are times 10 to the minus 19. 2.97 for Earth, 2.98 for Jupiter, and so on. Even Pluto, which has been demoted to a dwarf planet. So this is the planetary data. Here's some other. You can see the mass of the Earth is 5.97 times 10 to the 24 kilograms. The mean radius of the Earth is 6.37 times 10 to the 6. I don't remember what I used. Period of revolution in seconds. Extra credit. You convert the period of revolution into years. You can see Earth is 3.156 times 10 to the 7th seconds. You divide that by the number of seconds in a day, and you should get 365. But you can turn in a sheet of paper that just has these periods of revolution, and give me convert the period of revolution into years, and I'll give you some extra credit, okay? Most of the time, the people that don't need extra credit are the ones that do the extra credit assignment. So let's see who steps up to the plate. Okay, an asteroid is in a highly eccentric elliptical orbit around the sun. The period of the asteroid's orbit is 90 days. Which of the following statements is true about the possibility of a collision between this asteroid and the Earth? Well, I don't know the answer to that. The period of the asteroid's orbit is 90 days. Which of the following statements is true? I would say there's no possible danger of a collision. There's a possibility of a collision. There's not enough information to determine. I would just say it's not. I'm going to look up the answer. I didn't prepare for this question. And the answer is there's no possible danger. And the answer is from Kepler's third law in the given period. The major axis of the asteroid can be calculated. It's found to be 1.2 times 10 to the 11 meters. Because this value is smaller than the Earth-Sun distance, the asteroid cannot possibly collide with the Earth. Okay, I cheated on that when I looked at the answer. Okay, and we're going to stop there. We're going to next discuss gravitational potential energy. Let's see. All right.